We'll begin the webinar shortly. We're just waiting for some more people to join us. Meanwhile, please type yes in the questions box if you are able to hear my voice. We'll begin the webinar in 3-4 minutes. Good morning, everyone. My name is Tanmay Agarwal, and on behalf of MIDAS IT, I welcome you to this webinar. In today's session, we will be covering a brief introduction to MIDAS and its engineering solutions and rail structure interaction for metro bridges. So we'll basically look at the main concerns and considerations for rail structure interaction, and then I will generate a model in MIDAS Civil to show you how easily and effectively it can be done. So to start with a brief introduction to MIDAS, MIDAS IT is one of the leading CAE software development and engineering solution providing company in the world. Now, by engineering solution, what we mean is that we provide a strong combination of sound engineering tools in all sectors of civil engineering, that is bridges, buildings, geotechnical, as well as mechanical engineering, along with a very sound technical support and services. So talking about the areas of civil engineering that MIDAS covers, for bridge engineering, we have a specialized solution, MIDAS Civil. For more profound and in-depth finite element analysis, we have MIDAS FEA. Similarly, we have MIDAS Gen as the prime software for integrated design system for buildings, and MIDAS Design Plus as a specialized design tool. MIDAS GTS NX is a specialized software for geotechnical solutions like foundations, slope stability, tunneling, soil dynamics. And we also have SoilWorks, which is a two-dimensional solution for analysis and design of all the geotechnical problems. So, this is a list of our existing clients in India. As you can see, all the leading companies like AECOM, CH2M, Hill, L&T, Wrights, they are using MIDAS effectively. Apart from them, many government organizations such as PWDs, MES, they're also using MIDAS. And the leading universities like IITs, NITs, they are also our clients. So this was to introduce you to MIDAS. Now we step into the main gist of the webinar, that is rail structure interaction. Now the metro's transportation systems, it uses continuous welded rails. Why? Mainly because it helps in reducing the impact force, which ultimately leads to better ride quality at high speeds. And not only the metro projects, even the DFCC project, the dedicated freight corridor, even those projects, continuous welded rails are used. Now, what are the key concerns while using continuous welded rails? Since the rails are continuously welded, high amount of stresses develop at the joints for the cases of temperature rise and temperature fall. And this is because since no movement is allowed. And because of these stresses, the failure of the rails may occur. For the case of temperature rise, the buckling, and for the case of temperature drop, split webs. Now the key considerations for rail track analysis. First of all, it is very important to simulate the interaction between rail and deck. And for this purpose, MIDAS Civil has multilinear elastic links. Second, the consideration of all the loads, namely if we consider the horizontal loads, the loads due to temperature and the braking and acceleration of the train. Apart from that, the vertical loads due to train. The third is the load combinations. Now basically when we are going for analysis, there are two types of analysis that can be done here. Either separate analysis or complete analysis. I'll talk about this later in the presentation. Apart from this, MIDAS Civil has UIC code implemented and the sections for the rails are pre-feeded in the software, and for the expansion joints, in case the stresses and displacements are very high, then we need to provide the zero lateral resistance or the rail expansion joint members, and that can be done in MIDAS Civil. Now the continuously welded rail on the bridge is connected to the superstructure by the ballast, and thus the bridge and the track interact due to loading. When thermal loading is applied, expansion or contraction occurs in the bridge and the rail. Now that the rail is supported by a fastener cross-tie ballast, expansion and contraction is restrained, and accordingly axial force and axial stresses are accumulated in the rail. So as I was telling you about the two analysis methods, the separate analysis and the complete analysis. For the separate analysis, the thermal loading and the loading due to train are separately considered, while for the complete analysis, the loads are concurrently applied. Okay, so as we can see in this figure, if we go for separate analysis, then initially the loads due to temperature will be applied, and after that when the loads due to train occur, it will start from zero again. So basically the stiffness that we consider in this case will be an addition of both for thermal as well as for train. So when we go for separate analysis, in a way we are getting high axial forces. So in short, we'll be going for a more conservative design if we go for separate analysis. While if we go for complete analysis, after the consideration of thermal loads, the application of the train loads will start from that position. So the stresses and the displacement which undergoes in the rails after the thermal loads, from that position the loading of the train will start. Okay, so for the computational analysis, what are the key considerations for modeling? First of all, we need to properly model the multilinear elastic links, that is the interaction between a rail and deck. And that is a tedious job because we need to see which part of the deck is loaded, and accordingly there we'll place the links as per the loaded stiffness, and for the rest of the track we'll place the multilinear elastic links as per the unloaded stiffness. So a considerable amount of effort is required for modeling, providing unloading and loading stiffness, and of course it changes with the loading position of train. Apart from that, the complete modeling of all the spans for various positions of the train. So if we go for manual modeling, it takes up a lot of time. Now, how MIDAS Civil helps in this case? Using the rail track analysis model wizard, all models can be generated within minutes with each and every load. Now I'll take you to the live demo of the software. Alright, this is the working window of MIDAS Civil. First of all, we'll see that the initial temperature that we have defined here is 0 degrees Celsius. Now, rail track analysis wizard. Basically, in this wizard, all the images they guide you. They guide you to enter the information, the corresponding information, which will help you to generate the model. So, first of all, we need to define the material for our bridge and rail, and as well as the sections. So, I'll define some materials. The material for my bridge deck will be concrete as per the Indian standards. Consider M40 grade. Apply. For the rail, I'll consider steel as per the Indian standard. Okay. Next, I'll define the section for my deck. So, while defining the section, if we are considering metro bridges, they are mostly single cell PSC box girder. So, I'll define a section. Using this PSC viewer, you can easily generate the section. This is a dummy section that I'm taking, and as soon as I enter the values here, you'll see the section is generated here. And for the shear check, web thickness and torsion, these properties can be calculated automatically by the software. I'll save this model in this folder, and after we have generated the models, we'll see that the multiple models for various train loads will be generated automatically in this folder. Okay, so our section is generated. I'll just change the offset to center top. Okay. I'll also define one more section for my pier. So consider a solid rectangular pier and user defined. Okay. So I've defined the sections for my bridge and for my pier. Apart from that, I've defined the materials. Now I'll enter the values in the wizard. So bridge material M40 grade. Embankment. Now, when we are considering metro structures, even though we don't have any embankment, so it's we can just enter any value here, and after the model is generated, we can delete the embankment. For this case, I'll be modeling three spans of 50 meter each, and I'll consider simply supported condition. Although using this option, you can change the support condition for various spans. For the rail material, I'll consider steel and number of tracks as 2. Using this option additional check, you can define if there are any zero lateral resistance members or rail expansion joints. You can define their positions. Now the bridge section I've defined as deck, and the eccentricity between my rail and slab, let's say I'm considering that as 700 millimeter. As I told you, these sections are pre-fitted in MIDAS as per UIC 774-3R. So I'll just select this section and add it. Using this option, I'll define the positions of track with respect to the center line of girder. Okay. Now I'll copy this information for the rest of the decks. So both the decks have been selected. Okay. So as you can see, the information for all the decks is this. Next, I'll define the boundary conditions. For the boundary conditions, I'm defining the bearing type, and let's say I'm considering the stiffness of the bearing as 5000 kN per meter and the length of elastic link as 75 millimeter. Pier section, we have defined pier, material will be concrete, and the bottom of the pier is fixed. The height of the pier, which can be altered. Now, these properties for the ballast bed or the concrete bed, these properties have been defined as per UIC 774-3R. So let's say for longitudinal displacement limit 8 millimeter, the stiffness for unloaded condition 25, and for the loaded condition 50. Now in this case, either it's a ballast bed or a concrete bed, so you can add the properties and select whichever is the case, or using this option you can even select for, let's say, for a particular span you have ballast bed, and for the next span if you have concrete bed, so even that can be done. Apart from that, this guide, it helps you to see the boundary conditions at each and every place. Spring type, bearing type, embankment. Yeah. Next, I'll define the loads. Let's say the deck temperature is 25 and the rail temperature is 32. I'll define the loads for train. Vertical load. Now in this case, as you can see in these images, I'll define a load for the engine and for one bogie. This is just a trial case. So 140. Starting point I'll take as 10 meter, because initially, if you remember, for this case we enter 10 meter as the embankment length. So we have to consider the case when our train is on the bridge. So that is why I'll start the load from 10 meter. 10 meter. This is the bogie load. Now I'll define the engine load. Let's say 120 from 40 to 60. Now definitely when we are defining two tracks, for the worst case we will define the braking load for one track and the acceleration load for the other track. So for track 1, I'll define the braking load. And herein you can also enter functions. Let's say if we are considering 20% of the vertical load as braking load, so I can directly enter here and it will calculate it. So I've defined the loads for my track 1. Similarly, I'll do for track 2. The engine load and the bogie load. For this case, I'll define the acceleration load 20, and acceleration load will be applied only for the engine part. Okay. Now using this option, moving load data, I'll select 4 models. So that means I want to generate 4 more models, and the location increment for both the tracks I'll keep as 20 meter. So this means that for the next model that will be generated, these positions, the position of these loads, they will be at 20 meters ahead of this current position. So in that way, 4 more models will be generated, and for every subsequent model, a 20-meter increment in the position of loads for both the tracks will be there from the previous one. Okay. I'll define the element length, and let's say if we go for complete analysis and just select OK. Okay, so the model is generated, and as I told you, if you see in this folder, these models have been generated automatically. I'll show you the moving load positions for each and every model. Okay. This is the first case that we generated, and as you can see in this case, both for the unloaded case as well as for the loaded case, the model has been generated. And if we see the unloaded case, so in that case only the temperature load will be there, and for the loaded case we'll have the temperature load as well as the acceleration and braking load and the vertical load. So this is the position that we defined for the first case for track 1 and track 2. Now if we see the next model that is generated, wherein we have to do increment of 20 meters from the first case. So an increment of 20 meters in the train position has been done. Again an increment of 20 meter, and the last model is this one. So a total of 5 models have been generated. We defined this one. We defined the first model, that was this one, wherein the position of the loading on track 1 and track 2 were defined here, and in the subsequent models an increment in both the positions have been there for 20 meters. The second case, third case, fourth case, fifth case. So in this way multiple models have been generated and very quickly by using the wizard. So I'll just analyze, and this model is ready for analysis. I'll just show you the multilinear elastic links that have been created automatically. So when we see here, all the links have been generated, and if we want to see the stiffness of these links, that on what basis they have been created, whether a loaded condition or unloaded condition, we can just go to table and we can see as per the node numbers the stiffness will be displayed here. So for the unloaded condition we gave the stiffness as 25, and for the loaded we gave as 50. So that again can be cross-checked from here. I'll analyze this model now. The analysis is complete, and now we'll see the results. So I'll go to results and we'll see the stress profile, beam stress diagram. Let's say first we'll see for the unloaded condition when we are considering only the temperature loads. Unloaded condition, and we are interested in the axial stresses. Legend and apply. So in this way, since this was a case of temperature rise, so we are getting compressive stresses. These are the stresses in the rails. The stresses in the rails. So that can be seen here. Apart from that, if we want to know the value of stresses at any point, in any element, we can just go to result tables and beam stress. So for this summation load case, unloaded, and for all the elements of rails, we can see the stresses, the axial stresses, and these can be cross-checked with the limits provided by UIC 774 3R. Similarly, for the loaded case, this is the stress profile in the rail. Next, we are interested in the deformations that are occurring. So for that, deformed shape, let's say if I want to see for the loaded case, okay. So as you can see, for the first load case that we entered, this will be the deformed shape, and we are mostly interested in the relative deformation between the rail and the deck. So for that case, what we can do is, using this option, we'll see the node numbers, and we can see these node numbers 32, 33, and this. So using, now when I go to results, result tables, displacements, for the loaded case, displacement, so 32, 33, and this one is 34. So for this, we can just go there in the table and we can see the displacement, the Tx value, see it in millimeter. So 32, 33 and 34. So using these values, we can calculate the relative deformation that is occurring in this case, and that can again be checked with the limits provided by the UIC 774-3R code. And for all the models that have been generated, we can do the analysis and find out which is the worst case for the various positions of the load. Okay. So if you have any queries regarding this, please type in the questions box, and I'll try and discuss the queries in the session. Any queries by you can be entered in the questions box, and I will discuss those queries now. Alright, so we have a query that what about if the number of tracks is more than 2? So generally for metro structures, the number of tracks are 2 only, but even if the number of tracks are more than 2, then what we can do is, once we have already generated this model, so for this case I can just copy the rail track one more time. Basically here we have entered 2 tracks, but MIDAS Civil shows a single line. It shows the center line for both the tracks. So if I have one more track, I can copy this and enter it here. The applications wherein MIDAS Civil has been used. So for the Chennai Metro LNT use MIDAS Civil for rail structure interaction analysis, and even for Hyderabad Metro. Now, now I'd like to invite my colleague Mr. Nabil Ahmed. He will show you the wizard for PSC composite bridge. Over to you, Nabil.
So thank you, Tanmay, for that webinar. We are receiving a lot of questions from your end. So what we'll do is we'll type the questions and we'll send the text answers to you. And if you're not satisfied with the answers, you can mail to us the questions and we will respond back via tech support mail. So meanwhile, I would like to show you what if we are having like girder and slab kind of superstructure, what to do. So what we can do in that case, if you see over here, we have modeled a girder and slab type superstructure using a rail structure interaction wizard. So how we have done that is we have created a section, which is an overall section, the overall cross section, wherein we are having girder and slab, the overall cross section of the whole superstructure we have created as a uh, single line cross section. So this we will be taking in the wizard. So again, people ask us like what is the applicability and how it can be compared with the actual grillage model, wherein the behavior is different for different girders. So this has been compared with the grillage model, also the actual grillage model, because here if you see, so this is just a line model connected to the rails. So yeah, so this is just a line model connected to the rails. So actually in grillage model, the individual position of the rail will be connected and the axial deformations will be transferred accordingly, differently to different girders. So the overall results have been compared with the grillage model, and they have like come little bit different, but for ease, because RSI is quite a complex analysis involving long welded rails. So we need to create very tedious models. So for that case, one can do it this way. And since this has been compared, we can send you the comparison of this with the grillage model. So again, I would like to show you one more feature which has been recently introduced in 2016 version for modeling grillage, uh, the girder and slab type grillage model. So I would like to show you the wizard. So this is the wizard which has been recently introduced in MIDAS Civil to ease modeling of a grillage model. So a PSC composite grillage wizard can be generated, model can be generated easily. So I will just show you what all input we are taking for that. We are just taking a composite girder wherein the material definition for girder and slab has been done, as well as cross-sectional definition for the effective width of girder, and the overall girder dimensions have been entered over here. So also the material properties for girder and slab I am taking over here, and also the time dependent properties, the creep and shrinkage property for girder as per IRC 112, and also so we have defined the time dependent properties for the girder and slab. So the creep and shrinkage properties as well as the compressive strength properties. I would like to tell you that in RSI also we can include the time dependent properties of a cross section of our longitudinal section. For the superstructure, we can include the time dependent properties and those will be considered. So, but again, we'll have to define one more additional case with one more additional stage rather with the long term effects. We'll need to define the number of days as some 100 years for some 100 years, so that then we can consider the long term effects also in RSI analysis. So moving on, I'll just show you how we can generate very easily the pre-stressed girder and slab grillage. So this is the grillage wizard, and for the input, also we can use the spliced girder type over here, and as well as the overall precast girder type. So I'm going ahead with precast girder type. I will explain a little about spliced girders also. So the span and information I am giving two spans of 20 meters. The deck width I am taking 12 meters, and the spacing for the I am taking both the girders as simply supported. So I'm taking the gap between the girders as 50 mm, and the spacing from the girder end till the support I'm taking zero point 0.4 meters. And then over here, I'm modeling the substructure also. So the connectivity will be with respect to the elastic links, so which will simulate my bearing condition. So I'm entering over here, let's say I'm taking elastomeric bearing. So for that, I'm entering the Kx will be denoting the vertical stiffness, and Ky and Kz will be denoting my horizontal stiffness. Elastic length will be my thickness of the bearing. And then the various materials for pier cap and pier can be defined. Uh, the height of pier can be defined over here. And then moving to the cross-sectional definition, the thickness of deck slab can be defined over here, and the various material definitions for girders, deck, and diaphragm can be done from here. Also, the number of girders can be defined using this guide. So you can define a number of girders, and then the distance of the girders from the center line of the grillage. So that needs to be entered over here. Then for creating transverse elements, that transverse dummy elements will be created for the distribution of live load. So for creating transverse elements, you need to give the divisions or the spacing as per various options available over here. And then you can give multiple diaphragms along the length, and you can enter different cross sections for the diaphragms as well. And then also the length of along the length of girder, you can enter various cross sections. Also moving on, the tendon profile also can be generated from the wizard itself. So no need of entering the tendon profiles separately. So one can enter a curved profile or a halved profile as per the guide available in this. So various definitions for profile are available. So I'm going with a curved profile for both the decks with 3 tendons for the span 1 and span 2. And then moving on to the load application, the various loads can be applied by inputting the densities. The barrier load and the veining course load can be applied over here by inputting the densities. And moving load, it's better to apply it after creation of the model. So this option is not valid for the grillage wizard. So moving on to the construction stage. So this is the construction stage basically which we take. First, the girders are activated, and then the diaphragms are activated, and then over that, the part load of the slab will be kept over the girders. So that will be with the girder property alone. And then when the girder becomes composite, that is when the slab hardens, the composite property will be considered. So after that, the long-term effects and SIDL loads will be applied over the structure. So as I was talking about the spliced girder type, wherein the girders are brought in parts and stitched at the site. So for that kind of splice girder configuration, again, I can show you this is the construction stage that we follow for the spliced girder type. So as per this, the various construction stages CS1 to CS8 will be generated. So when I click on OK, so you can see that within no time this model is created. And if I just show you the stage-wise model, so stage 1 is the stage 2 wherein just the girders are there. In stage 3.1, if you see over here, the wet concrete load is activated over the girders. And then stage 3.2, the slab is activated. And then stage 4, the additional loads, barrier loads, and utility varying course loads. So superimposed dead loads are activated, and the fifth stage will be for long-term effects. So this is how very easily you can generate a model using pre-stressed concrete composite bridge wizard. So we would like to have your suggestions your questions for the upcoming webinars so that it can be of great help to you. So please let us know your questions and we will be answering your questions via emails if they have not been answered in this webinar. So thank you for attending the webinar, and you can post all your doubts at techsupport@midasit.com. Thank you.